Welcome to the APL Quest. See APL Wiki for details. This is the 7th problem from the 2016 round of the APL problem solving competition. We are to take a list of numbers and filter it such that the only numbers that remain are those that can be cleanly divided by either 3 or by 5, or, well, by both. Let's get started. First, let's create some data that we can test on. So here's some integers, and just for the fun of it, let's also have some numbers that are not whole numbers. Okay. Before we go to look at what actually is divisible by 3 or 5, let's have a look at a very special feature of APL, which is called the outer product. Conceptually, it's actually really simple, and especially in its basic form where we just give it two lists. So here on the left we have a list of numbers, and over here on the right we have another list of numbers, and all the outer product does is make a combination from all the combinations of every element on the left with every possible element on the right. In other words, we're making a table of such combinations. The most common example of such a table would be a multiplication table. And the syntax in APL for making a table or an outer product is this jot and then a dot, and then we put in the function that we want to make the table for. So a multiplication table would be jot dot times. And here we can imagine that we have the headers going down the left side and across on the top. So 1, 2, 3, 4 on the top and 10, 20, 30. We also see the 10, 20, 30 because we're multiplying them by 1. Now instead, we can use a different function than multiplication. In our case, we want divisibility. Now there isn't a divisible by function in APL, but there is a remainder. That is, if you divide, how many do you have left over after you try to distribute evenly with whole numbers? And so we can take our numbers, and then we can take 3 and 5 on the left, and create a divisibility table that shows the remainder whenever we're dividing. So here you can imagine 3 and 5 going down, and these numbers 1 through 16 across, we can see that the remainder is 0, 1, 2, 0, 1, 2, 0, 1, 2, because we keep adding 1 for when it comes to 3, and 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on for 5. And then we can see that for numbers that are not wholly divisible, then the non-integer part, the fractional part, is also part of what remains, because we cannot divide that cleanly. You can see that the 3 went away from 3.5, but there's a half missing, whereas for 5, the whole 3.5 is the remainder. And so something is divisible if the remainder, when you try to divide it, is nothing, if there's nothing left. That is, if we have 0. So we can compare 0 to this, and APL uses long right scope. What does that mean? It means that the equality function takes as right argument whatever is everything that's on its right, all the way to the end of the expression. And so we don't need any parentheses here. And so we have a table that shows us a 1, which means true in APL, whenever something is divisible, and a 0 when it's not divisible. And we're not actually interested in whether or not it's divisible by specifically 3 or 5. We just want to know if it's divisible by any one of them. So we want to say, yes, keep this number if we have a 1 at the top, or we have a 1 at the bottom, or both. And we can do that by using the OR function. And we're inserting that, and we're using a slash bar after that. It means a vertical reduction. So we are sticking an OR in between, so to say, the space between the first row and the second row, and that reduces this two-dimensional array, which you can see is two-dimensional by these axis arrows, and it reduces to a one-dimensional array. So here's a mask indicating from the numbers in this variable d which ones are divisible by 3 or by 5. And we can use this then to filter, and we do that with a slash. So we filter d, and that gives us just the numbers that are divisible by 3 or by 5. We can actually get rid of the parentheses if only we had a function that was like the slash, but with swapped arguments, which isn't built in, but we can construct it with a higher order function called commute. And it looks like this frown, because it's all getting confused which side is what. And then it modifies the function on the left to swap its arguments. So here we have exactly the same thing. And finally, we can make this into a function, which would be our solution to the problem, by substituting a special symbol, which is the Greek letter omega. That's the rightmost letter in the Greek alphabet, indicating the right argument. So that's whatever is over here on the right, in this case d. And that solves our problem like this. And we don't actually need this much white space in our code. And so if you prefer, we could get rid of all of that. Of course, we need a space between 3 and 5 to separate them. So we can write it like this as well. Thank you for watching.